So let's say on a Cartesian plane, I have two curves. One of my curves is a quadratic, which does something like that. And the other curve is just a straight linear line, which just comes through here like this. And I'm asked to find this shaded space in the red here. Well, if I pick this point here and this point here where they intersect, if I do the yellow one first, if I calculate the total area under the linear line from my lower bound to my upper bound, so my dotted region there, I'm going to be calculating all of this area in the yellow highlighter. Likewise, if I use the same bounds, but I only did it for my parabola, my purple curve, I'm going to be calculating all of just this area under here. So if I take one away from the other, so the linear line has more area underneath in the yellow. If I take the purple area away from the yellow area, I'm just left with that red area, which is where they are the area that's bounded between these two curves. So this point here and this point here are what I would use on the bounds of my integral when I'm solving for the total area bound between each curve and the x-axis. And I can find those because they're the points of intersection. So that's when one curve is equal to the other curve. So let's take a look at an example. We'll come down here. Let's say that we're asked to find the area between f of x, which is just x squared, and g of x, which is just x. So let's see what this looks like on a graph. So if I take a Cartesian plane, like so, then my x squared is just this parabola here. And the equation g of x equals x, or just y equals x, that is going to be this line here. And they're going to intersect somewhere. And what I'm looking for is I'm looking for this area in here. So first of all, I need to find the points in which these two are intersecting. And I can do that. So my points of intersection, or POI, that is when f of x is equal to g of x. So in other words, that's just when x squared is equal to x, which by inspection, just looking at it, we can see that that is when x is 0 or when x is 1. So here is when x is 0 and here at x equals 1. So if I calculate the total yellow area, so the total area underneath my linear line, so all of this in yellow space here, well, that is going to be the definite integral from 0 to 1 of my g of x, my yellow line, so that's just x, with respect to the variable x. So if I crunch these numbers, if I anti-differentiate x, I just get x squared over 2, and I need to do that from 0 to 1. So I substitute these in, and I get a half when I put the 1 in, subtract, well, I get 0 when I put the 0 in, so I'm just left with a half. Now, if I want to work out the total area underneath the quadratic or the parabola, so this purple or this pink space under here, I use the same bounds, so I might do this over this side. I anti-differentiate from 0 to 1, but this time I use my x squared because it's the purple graph, so it's the parabola. And well, here I end up with x cubed over 3, and I'm doing that from 0 to 1. When I substitute the 1 in, I just get a third, subtract. When I substitute the 0 in, I just get 0, so I'm just left with a third. So the total yellow area is a half, and the total purple or pink area is a third. So the red area, the area bound between these two things, so this area in here, see if it'll let me draw it, that area is going to be equal to a half minus a third. And well, a half minus a third is just 1/6. So we have 1/6 units squared of total area bound between these two curves. Let's take a look at another example. So this time we're going to be looking for the area between f of x, which is just x cubed, and g of x, which is 4x. Now, if we think about what this might look like on a Cartesian plane, in purple this time I'll do my x cubed, and in the yellow I'll do my linear line, my 4x. Well, x cubed does something like this, and 4x is going to go through the origin with a gradient of 4, so there's going to be an intersection somewhere there and an intersection somewhere down here. Now we can check that that's true, because if we calculate for my my points of intersection, well, remember that's just when f of x is equal to g of x, so we're calculating when x cubed is equal to 4x. Now again, by inspection you can kind of look at this and you can see that, well, if x is 0, that works. If x is 2, that also works, because I get 2 cubed is 8 and 4 times 2 is 8. Or when x is -2, that will also work, because I'd get -8 on both sides. So we have intersection points here at 0, here at 2, and here at -2. Now, what's really important for this problem, which will save us a lot of time, is that this thing is symmetrical. So if I just calculate the area between 0 and 2, and I double it, then I'm going to get the total area, all of this stuff here, in red. So I'm just going to look in the first quadrant, and I'm just going to look between 0 and 2. I'm going to calculate that red area, and then if I double it, I'm going to get all of the total area bound between these two curves, because it is a symmetrical graph. So what do? Well, I take my bound, so I'm here at 0, and then I also look up here at 2, and I calculate all of this yellow highlighted area underneath the linear line here. So it's all of this space. So the way I calculate that is I do the integral from 0 to 2 of 4x with respect to the variable x. And well, when I do that, I end up with just 4x squared on 2. So I just get 2x squared. When I integrate 4x, I do that from 0 to 2. I substitute my 2 in. I end up with 8. Subtract, well, I get 0 when I substitute my 0 in. So I'm just left with 8 total units squared of area shaded in the yellow there underneath that yellow curve. If I do the same thing for the purple curve, that x cubed, I will then end up with this pink space underneath here. So I can do that if I leave ourselves just enough room over here. I integrate from 0 to 2 x cubed with respect to x. I end up with just x to the power of 4 over 4. And I can do that from 0 to 2. So when I substitute 2 into here, 2 to the power of 4, that is 16. Divided by 4 is just 4. Subtract, when I put the 0 in, I just get 0. So I end up with 4 units squared of area underneath in the pink there. So if I want the total red space, so the red area, which is the area bound between the two curves, which is what I'm looking for, that's going to be 8 minus 4, which is just 4 units squared of area. But we've also got 4 units squared over this side on the in the negative space. So the total would be 4 times 2, which is 8 units squared of area. Now, if this wasn't symmetrical, then I would do this bit first. I'd get an answer for that red area, and then I would do this bit second, and I would get an answer for this second part, and then I could add them together. But the beautiful thing about this question is that it is a symmetrical graph. If we look at one more example, and this one is slightly harder, let's take a look at the area between. So if I get my first function, f of x, which is just x squared, and my second function, g of x, which is 2x squared minus 2x. Well, let's get a little bit of an idea on what this might look like. So here I'll do this one in the purple, and I'll do this one in the yellow. Let's draw a Cartesian plane. Now my x squared, that one's nice and easy. That's just my standard parabola. But this one over here is going to be a little bit steeper because of the 2x squared, and it's going to be translated to the right. So it's actually going to look more something like this. Now we can check that by looking for my points of intersection. So let's calculate our points of intersection. Well, that is when f of x is equal to g of x. So that is when x squared equals 2x squared subtract 2x. So we're looking to find out now when 0 is equal to x squared take 2x. I've just subtracted x squared from both sides. I can factor out an x, so when 0 is equal to x outside of x take 2. So that happens when x is 0, or it can happen when x is 2. So this point here is happening at 0, and this point here is happening at 2. Now we've kind of got to break this question down into two separate parts. The first part is just looking at this area bound in here, okay? And then we're going to look at the blue area afterwards, which is just this area bound here. And then if I add the red and the blue together, I would have the total area bound between these two curves. So just looking at the red part first, well, that's very similar to the questions that we've done before. So if I integrate from 0 to 2, and I do the one that's sat on the top, so that's going to be my purple graph is above. So we're kind of integrating all of this space now in total. So it's going to be all of this. And then we're going to subtract away just this little yellow bit in here, which I'm kind of trying to draw in there. Okay, so if I do the purple one first, so that's just my x squared with respect to the variable x. Well, that is just x cubed over 3 from 0 to 2. So I just end up with 8 over 3 there. And you can check that definite integral, but when you put the 2 in, you end up with 8 over 3, and the 0, you just get nothing. When I do the same integral from 2 to 0 for 2x squared take 2x, so I end up with 2x cubed over 3 subtract x squared, so just adding 1 to the power, dividing by the new power, so you can check that, from 0 to 2. Now I'm lucky because when I put the 0 in, I'm going to get nothing, so we'll save that thought for later. But when I put the 2 in, I just get 16 over 3 subtract 4. And well, I'm just taking away that 0 afterwards, so easy as that. 16 over 3 subtract 4, well, when I do that, I just get 4/3. And you can check that. If you convert that 4 to a 12 over 3, then 16 minus 12 is just 4, so we end up with 4/3. So the total area that I have bound between these two curves is going to be the big one, which is the purple area, subtract the little one, which is the yellow area. So I have 8/3 minus 4/3, which is just 4/3. And that is my red area, which I kind of tried to shade in at the start, which if I erase some of this, oh, if I kind of draw that back in, that red area is just this area here, which we just calculated. Okay, so we did from 0 to 2, we did the larger area, the purple, the x squared, subtract the smaller area, the yellow, the 2x squared minus 2x, and we ended up with 4 over 3 units squared of area. But now we have to do this little blue bit. Well, this blue bit is just the area bound between the yellow curve and the x-axis. So if I can find this root here, then I would just have the 0 as my lower limit and whatever this number is up the top here as my upper limit. So we need to work out when there are roots of my yellow function. So 2x squared minus 2x, remember roots are when this is equal to 0. If I factor out a 2, I just get x squared minus x is 0. So I need x squared to be x. So if I just divide by 2, add x to both sides. So that is when x is 0 or x is 1. So I have my 0, which is one root, and my 1, which is another root. So if I want that blue area, I'm going to need to integrate from 0 to 1 my yellow function, which is my 2x squared minus 2x. Now we integrated this over here, so we know that this is just 2x cubed over 3 subtract x squared, and I need to do that from 1 to 0. So when I put the 1 in, I just end up with 2/3 subtract 1, and when I put in my 0, I just get nothing. And 2/3 subtract 1, that just gives me -1/3, which makes sense because if you look over here, I'm underneath the x-axis, so I would expect to get negative area. But for our purpose, when we're talking about area, we don't really have negative area, so we just say 1/3 units squared. And that is that blue component which we've just calculated. So if I add the red and the blue together, if I add 4/3 and 1/3, my total area would be 5/3 units squared of area bound between these two curves, the yellow and the purple there. So that one there's quite a tough question, but definitely one that's worth going through. You might want to watch it once or twice just to fully get the hang of exactly what's going on there. But that is how we calculate the area between two curves.